Great. So Fabrizio is gonna give us his talk here, continuing the trend of modeling financial services. I need to use the mic, and I think he's really taken one for the team, and from a fashion perspective, been carrying the conference on his back all week. So I approve. Thank you. Thank you for your service. And take it away.
Okay, does this, oh, it works, fantastic. Okay, so first of all, an announcement. These slides are being set up going across like 3 different virtual machines on my computer. I am already 91 degrees Celsius hot, so if the computer melts and you don't see anything at some point, you know why. Okay, so, yeah, sorry, internet, like, you know, computer stuff, okay. Okay, so what is the problem that we are trying to solve? Just a quick survey, who's familiar with blockchain technology? Have you ever used the thing? Okay, cool. So basically, if you work in Ethereum, or if you like Ethereum, or if you use Ethereum, you have some landmark places that you should know about. So the first one is the dark forest. There's a bit of echo. Is it normal? Like, no. Okay. Anyway, so there's the dark forest. The dark forest is basically where your transactions end up before going into the blockchain. Is where they wait to be mined, and that's the land of scary arbitrageurs that basically try to profit from your transactions. The reason why this is important is that when you see the network being congested and the transactions fees going up, usually is because something is going on in the dark forest. Basically, I don't know, like an NFT drop comes out or stuff like that, and people try to arbitrage on top of that, and they drive the fees high. The second landmark place in Ethereum is the gas station. It's basically the fact that transactions need gas to be executed. What is gas? Gas is just the fees that you pay for the transactions to be mined and included in the transactions, in the blockchain. Now, these two things go hand in hand. So basically, when fees are high, it's because something is happening in the dark forest. And you know, this brings us to this problem. So if you say, okay, I want to submit a transaction, the cost to submit your transaction is given by a very simple multiplication, is the price of gas and the size of gas. The size of gas is the amount of computational power your transaction needs to use to be executed, basically. And the gas price, as I said, it's driven by factors like network congestion and stuff like that. Okay, so this is how much you have to pay to submit a transaction. And now you say, okay, one thing that I may be willing to do is I would like to buy the gas price today to use it tomorrow, basically. So I want to do future gas price reservation. So the user wants to do it to hedge against fluctuating gas prices, and the gas seller, that is basically the block miner, may be interested in doing the same to, again, hedge against fluctuating gas prices. So the question is, can we do that? There is a solution that is basically using this mechanism here that is called future gas price reservation mechanism. So the idea is basically this. You have 2 different phases. The first one is the setup phase, and the second one is the execution phase. The idea is that in the setup phase, you want to reserve the gas, and in the execution phase, you want to use the gas. So the green boxes where it says natural draws is basically the gas price in the future. So the idea is that when you see P exec, that is the gas price at the moment where you have to execute your transaction. So the idea is you start at the init LH. This protocol is called ledger hedger, by the way. You start at the init LA phase, and the gas buyer has basically 2 different choices. It can not use the protocol, or it can decide to use the protocol. So if you don't use the protocol, you just wait. What happens is that then, you get to the point where you actually want to deploy your transaction. The gas price is known at this point. Nature draws the gas price. And then the buyer can decide to either publish the transaction that then gets executed at market price, or to not publish it at all and just basically do nothing. The other thing that you can do is that you can initiate the protocol. And so what happens is that you say, hey, I want to buy some gas, I want to reserve some gas, and you specify a price. At this point, the gas seller needs to decide to accept or decline this offer. In practice, this is made by using some smart contracts in which basically you escrow your funds. So you say, I want to buy this gas, and you put some crypto in the contract, and it's locked it's locked there until the execution phase finishes. So at this point, the seller can see the offer and decide to accept or decline. So again, if the seller declines the offer, what happens is that at the execution phase, the buyer can decide to recap the money that he put in the contract for the gas reservation, or to forfeit it. That basically means the buyer leaves the money there and loses it. Okay, so now instead, if the seller accepts, we go into the publish transaction game. So the publish transaction game is where, the buyer must actually provide the transaction to the gas seller to be included on chain. And now there is a problem, that is, I give the transaction to the seller, but how can I be sure that the seller will actually include the transaction? After all, the seller has been already paid, it's already seized the money in the contract. So there are two things that can happen. The first one is buyer doesn't provide the transaction. So it basically doesn't give the seller, the transaction that should be included. In this case, the seller has this procedure called exhaust, that basically means it fills the kind of block space, the gas space that were reserved, with BS data, basically, with just like, null calls, basically null contract calls. In the other case, the buyer publishes the transaction, and now the seller has, again, three options. So two options are, as in the fulfill no transaction case, so the seller can either exhaust the space or just ignore the contract altogether, or it can just include the transaction. The idea is that if you ignore, if the seller ignores, it loses a lot of money. It loses all the money in the contract. If it exhausts the contract, the seller gets the money from the contract minus a tiny epsilon. And if the seller confirms, it gets all the money from the contract. So the idea is that we make the confirm case marginally better for the seller than the exhaust case. In this case, if the seller doesn't have the transaction, it's not big deal, it's still getting paid. If the seller gets the transaction, it still has a marginally higher payoff in including the transaction data. So this is the protocol. And if you decide to basically develop this thing and deploy it as a service on the blockchain, you introduce a new player in doing so. So now you have the platform provider, that is the one that is actually, administering this platform, and presumably will get the fees from, buyers and sellers that decide to use this thing. So we at 20 Squares, we do basically mathematical modeling, game theoretic, incentive alignment, mechanism design, all this kind of stuff. We were approached by Manifold Finance, that is a very big player in, the MEV space, in Ethereum and all this kind of stuff. And Manifold Finance in this picture is basically Leonardo DiCaprio that says, we are thinking about developing this service. So, we have a very simple question. Does this make us money? And basically, they tasked us to find out in which market conditions buyers and sellers would have an interest in using this thing, because you don't want to pay hundreds of developer hours and assume a lot of risks to basically do this thing, and then no one uses it. So they asked, and we tried to find out. So how did we do that? Well, we used open games that I guess a lot of people here have, hear presentation about that like again and again and again. So I will be very quick about it. This is an open game. It's a box with 4 wires. The idea is you observe stuff in X. So X is the stuff that you observe. Then you decide to act on the stuff you observe and you output a Y. Then you get the consequences of your action in the wire R. So from the future, you get the payoffs of your action. And S is basically the portion of the consequences that you have to back propagate to someone else in your causal past. You can compose these things. You can tensor these things. You can do actually real things with these things, in the sense that this is an implemented formalism at this point. We have a DSL embedded in Haskell. It can be installed easily using Nix flakes. So if you have like NixOS installed or Nix package manager, that should be an easy thing. It's free available, free to use. And at the moment, we have used it successfully for the analysis of staking protocols, token design, and also applications outside of crypto. So let me give you an idea of how the DSL works. This is probably more interesting for the programmers here. So you declare an open game by using this kind of thing, and you say, okay, inputs is the X wires, feedback is the S wire, output is the Y wire, and returns is the R wire. Okay, and then you have the internals of the open games. So what it means is, internally, all these 4 wires are duplicated. I will show you why in a second. And then you have this thing here. This is called like dependent decision. This is what the actual game does. So you can plug a few different things there. You can plug a dependent decision that is a strategic decision. So basically you observe something and you have some strategy and you decide to output something based on that strategy. You can have a function in there. A function is just like a non-strategic decision. So you have no strategy. You observe something and you deterministically do something with it. And then you can also plug another game in that. And so this allows you to, do nested game composition, basically. So to give you an example, this is the prisoner dilemma. Josh showed this image as well, but that's the counterpart in code. So you see, this game as a composition has no wires. So that's why inputs, feedback, outputs, and returns are empty. If you go into the inside of the open game, we see that we have 3 different sub-games that are player 1, player 2, and you. So player 1 and player 2 are the players of the prisoner dilemma. They do not observe anything and do not backpropagate anything, and that's why they don't have wires on the left. But they output a decision, and they receive a payoff in the form of returns. And the decision, as you can see, is just like, deciding between cooperate and defect. The outputs of these 2 players become the observations of the U player that is the payoff matrix. So this will be a completely deterministic player. That's why the operation is forward function. And what this U game does is it observes the decision, it applies this forward function that is just the payoff matrix of the prisoner dilemma game, and it spits out the payoffs for the player. The payoffs are spat out as outputs, but we have basically the caps internally in the category of open games. So these things can be automatically understood behind the curtains to be feedbacks, and so they are automatically fed to the returns of P1 and P2. Okay, so this is basically the idea of open games. And now let's try to show a little code demo. So let's see. So this is the code here. We use basically almost always the same file structure. This is freely available online. I'll drop, there's the link in the last slide that I'll show you. So basically, the model consists of a few files. Main.hs is basically the kind of final app that you can execute. Then you have like, in action spaces, let's start maybe with components. So components are all the sub-games that you need to model the thing. So for instance, in here you see the natural draw thing, this green box. This is for us gas price distribution. So this is just a nature distribution that is basically a Gaussian thing that will spit out a gas price with a certain probability. Then we basically defined all the different sub games that you need to. These are basically recoup, LH, buyer, all this kind of stuff. They are like really, we just took this picture basically and implemented in code, more or less as you can see, as literally as you could do it. In here, you see that many of these games have like a boatload of things going on. These are basically what we call exogenous parameters. So these are things that maybe you want to define either at runtime or you don't want them to make directly part of your game. So for instance, the wealth buyer and wealth sellers are things that you do not see directly in that diagram. But the idea is that if I don't have any money, I won't be able to broadcast a transaction no matter what, because I won't be able to pay for the gas fees. So when you try to actually run this, in a computer, you have to take into account all these nitty-gritty details that basically weren't there in the original thing. Another thing that we had to take into account is that players must have an intrinsic utility for the transaction they want to broadcast. Like if for you the transaction is worth absolutely nothing, the best strategy is do not do anything. Do not use the protocol. Do not even broadcast a transaction at market price, because basically you don't fucking care. So why should you do that? Instead, if you have an intrinsic utility, the idea is, okay, I may pay some fees, but I will get the intrinsic utility of the transaction in doing so. So we have all these components. And then we slap them together in this model.hs thing. So in here at the end, you have like the complete game that runs. This is basically the whole kind of diagram. In parameterization, we define some parameters. So again, for instance, the fees, the starting gas price at setup time, and all these kind of things. In strategies, we define the strategies for all the players, actually for all the games, because as I told you, each game has strategic, can have a strategic decision. You can put a strategic decision inside each game. This means that every game that is strategic will need to be fed a strategy. Open games, the way we use them are naturally Bayesian. So this is why our strategies, they all have this weird signature with like the, Kleisli stuff, is because in the end we are using probability distributions everywhere. I have 5 minutes or, okay. So we have that. Then we have other stuff like types and blah, 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 but let me go directly to trying to simulate this stuff. So if I give Nix develop, this thing will open. Now I am in the Nix environment, so I can use stack GHCI. This is basically Haskell magic. Now I really have to hope that it doesn't recompile all the engine. It does not, luckily. So if I execute the main function, it will basically try to evaluate the game with different parameters. So what does this mean? You see 90, 91, 92, this is basically the kind of gas price at execution time, we assume that a setup time, the gas price is 100. So this is going from 90 to 110. When you say false or true, that means it's true when the players have an interest in using Edge Ledger, and it's false when they have not. So this is running two different evaluations. The first one is at zero costs. That means it doesn't cost any fee to use Hedge Ledger. The second one is it costs some fee. So hopefully like Leonardo DiCaprio, that is Manifold Finance, gets some money with people using this stuff. You can also have an interactive main where I don't remember now precisely the type. So let me check. So, okay, you have to specify the double, that is the contract price at execution time. So let's say that it's 100. And the two payoffs, let's see if it says something here in main. Oh yeah, this is the utility parameter for buyer and seller. So what it means is this. We basically found out that this buyer and seller have an interest in using this stuff only if they are risk averse. Risk averse basically means something like this. Imagine that I flip a coin and I say, you know, like 50% of the times it will be tails, 50% of the time it will be heads. I can tell you, either you get $50 right now with certain probability, or you play the game and you can get either 100 or 0. And if you calculate the expected value, these two games are completely equivalent. A risk-averse player will prefer to get the $50. A risk-loving player will prefer to play the game. So the idea is that if you want to hedge, you don't want to risk. So you have to be, you are risk-averse. We found out that if you are not risk-averse, you are not going to use this thing. So in here, I can put some parameters that quantify the risk aversity. So in this case, you see it's always true. If now I specify some risk-loving players, even in a situation where the gas price doesn't fluctuate, they have no interest in using the thing. So with this model in mind, we were able to reply to Manifold, and no, provider, this thing won't make you any money for a very simple reason. Buyer and seller are trying to hedge against different things. Buyer wants to hedge against rising prices. Seller wants to hedge against falling prices. Now, in contexts that are highly symmetric, basically buyer and seller have access to kinda the same information. And it's very unlikely that, you know, two players observe the same thing and they get to radically opposite opinions about what is going to happen. And, you know, Manifold concluded that, okay, there is not enough market for us to develop this service. They shelved the project and instead they decided to become an Ethereum validators, and they're doing really, really, really well at the moment. And yeah, that's it. So we were able to simulate this thing using open games, using the compositional nature of the game. It made prototypation very fast. And yeah, that's it. You can scan the code if you want to look at the repo. It's fully documented and everything is there. Thanks.
You're up next. Can you start setup? Okay, we have about 5 minutes for questions. And I will run you this mic and you can answer with that mic.
Just the summary of your conclusion there. It won't happen because people are wanting to hedge in opposite directions. Doesn't that mean stock markets shouldn't work? People sell things because they think the price is going to go down, and other people are buying them at the same time because they think the price is going to go up.
Yeah, but the problem is that the stock market is infinitely more complicated, and most importantly, not everyone has access to the same data. A stock market often works with, you know, very asymmetrically informed players that profit off, you know, the poor dumb idiots that, you know, hope for a better life, which is why it's an intrinsically toxic place. Instead, in this case, the information is like, imagine that there is an NFT drop coming up. The gas price will be will go up. Everyone knows that. Buyer will never use this platform in that setting. So that's the problem. You know, it's a much more contained setting and much easier to predict.
Okay.
Thanks, Fab. Are you, do you have any interesting clients outside of blockchain, or do you have any experience with those clients, or is it just historical reasons that you're working in that kind of environment?
So the reason why we are working with blockchain mainly is because we try to, sell open games as a convincing tool to economists for ages, and they really didn't care. The blockchain has the advantage that it's a very open-minded system. This thing has been supported by an Ethereum grant. They were the first ones to believe that this thing had practical utility. In general, we are not biased, for blockchains. We work with anyone. We are in talks also with like insurance companies and stuff like that. The problem is that usually these companies have super long workflow. They have to like talk with their boss and the boss of their boss and all the way up, and it takes a year. Like this project, we literally were cold mailed by Sam Bacha from Manifold Finance saying, hey, I need help. We jumped on Telegram, and a week later we had the contract signed, money in the bank, and we were able to start simulating. So it's just like if you're a small startup, that makes a huge difference. Like honestly, we cannot afford, dealing for a year with a client. It's just like crypto makes things faster. But yeah, in principle, we are in talks with non-crypto players, and God willing, at some point, something will come out of it.
Thanks.
I had a question about connecting. These are models of the incentives of the people, but there's also a lot of work on models of the correctness of the protocols.
Yes.
So how do these two like different aspects of modeling connect to each other?
So one very interesting thing that we can do, and this is kind of what we did here as well, is you give us your like protocol, let's say, and suppose that there are some parameters that you have to fine tune, right? And you don't know precisely what's the best way to do so, but you know what behavior you think people should use with your protocol. What we do is we do everything by the book. We verify that the expected behavior is indeed an equilibrium. And then what we can do is we tweak these parameters slowly and steadily until we start seeing strategic deviations. So in that case, what we can do is we can tell you within this range, the market or the users have an interest in using the protocol as you intended. Standard example is stablecoins, where basically you rely on incentives so that the market defends the peg of your stablecoin. Usually the way this works is if you're like peg to the dollar, everyone is happy. You go to 99 cents and everyone's like, okay, it's going to go up again. 97, when it's like at 85, people are like, okay, oh, fuck this shit. Like they sell everything and run away as fast as they can, and you are doomed. So the idea is, in this case, we can try to quantify this bound and basically give you a bracket where people start losing confidence in the peg. And then you can use this to tweak like interest rates and all this kind of stuff to be sure that the protocol works as intended. Doing mechanism design in the super general sense of like finding the mechanism, that is more an art than I would say a science. So it's more difficult.
Great, thanks. I think we'll get started with Toby.
So I need to share this.